Alright, so this chapter is called Electrons in Atoms, so the main focus is really figuring out where electrons are in atoms. It's broken up into a couple of sections. You might recall things like an atom has a nucleus, protons, neutrons, electrons, and right now we're actually going to go into a very brief evolution of the atomic models. So let's go back a little bit, like 2,400 years ago. Back to ancient Greece, where all the Greek philosophers just sat around all day and thought about thinking. And they thought of matter and they wondered what that was. More specifically, what it was made of, what the world around them was made of. We're obviously going to start with the Greek philosopher, Democritus. He suggested that the material world around him, all physical material, physical matter, was made up of tiny particles, which he called atoms, and empty space. And he also believed that depending on what the substance was, the atoms that made them up varied in different sizes and shapes. For example, some atoms might be smooth, some atoms had hooks on them, or some atoms were rough, or some atoms had spikes on them. And it was these little physical differences on these atoms that contributed to the properties of the matter that they could see. Of course, this was all thought experiments. There was no scientific experimentation done. It was just all thought of. And of course, this idea that Democritus had was opposed by several philosophers, including Aristotle. Aristotle basically just says, nope, all matter around us are comprised of four elements: fire, air, water, and earth. And of course, everybody sided with Aristotle, and moving forward, this four-element theory was favored, and most scientists followed suit with this for about 2,000 years. Until this guy reboots the idea in 1808. He was an English Quaker, he was a teacher, he did work in meteorology, in chemistry, in physics, in color blindness. But most importantly, he gave Dalton's atomic theory, which you might recall includes a couple of postulates like all elements are made up of atoms. Atoms of an element are all identical. Atoms of different elements are different. Atoms of different elements combine in simple whole number ratios to form chemical compounds. And in chemical reactions, atoms are separated, they're combined, they're rearranged. He also noted that common substances always broke down into the same elements in the same proportions. And this concept became pretty popular. This was a very large scientific advancement. And this was in 1808. We didn't really have the next major advancement until a couple of years later. In 1897, this guy discovers the electron. Now you might remember the experiment he used to do that. It was called the cathode ray experiment. So basically, Thomson performed experiments that involved passing electric current through gases at low pressure. So he sealed gases in glass tubes fitted with these metal discs called electrodes. The electrodes were connected to a source of high voltage electricity. So what that would do is one metal would become positively charged, the other one would become negatively charged, and this glowing beam would form between the electrodes, going from the negative electrode to the positive electrode. And so he figured out that these cathode rays were attracted to electrodes or plates that were positively charged. If he used plates that were negatively charged, he'd see a deflection in the cathode ray, which is what he called it. Well, I don't know if he called it a cathode ray, but after seeing the deflection of the cathode rays, And him knowing that opposite charges attract and like charges repel, he proposed that the cathode ray was basically this stream of tiny, negatively charged particles that were moving at extremely high speeds. He would do experiments that would allow him to measure the heat generated from these cathode rays. He would measure how much they would be bent by magnets, and basically he was able to estimate the mass of the rays, and it turns out it was like 1,000 times lighter than a hydrogen atom, which at the time was the smallest thing that they knew. So he called these things corpuscles, which today we know as electrons. So he basically just upgraded Dalton's model, because Dalton's model said that the atom was the smallest particle, indivisible, and after J.J. Thomson's experiment, we find out that there are smaller things found in the atom. So when it came to proposing a model for the atom, he did know the overall charge of the atom was neutral. So he pretty much thought that atoms were these uniformly packed, positively charged spheres of matter with these sort of electrons distributed throughout the atom. And of course, hopefully you remember that this was called the plum pudding model. But this model wasn't going to last too long, because one of his very intelligent pupils, in his attempt to learn more about the atom, performed a very popular experiment with a foil sheet made out of your favorite element. In 1909, Rutherford performs his very famous gold foil experiment. So as Rutherford tests J.J. Thomson's experiment, he believed that if he fired these very, very tiny, positively charged particles at a very thin sheet of gold foil, then these particles that are being fired at it basically should just pass right through and keep going straight. There shouldn't be any deflections. If there were, this sort of deflector screen would pick up those deflections. But as it turns out, that was not the case. Most of the particles did go straight through, but occasionally you had deflections, and in some cases very extreme deflections. So this led him to believe that the atom was not exactly how J.J. Thomson described it. So he proposed something else. Rather than the atom be this big positively charged blob of matter and electrons distributed through it, he proposed that all the positive charge was located in the center of the atom. So we had something like this. All of the positive charge was extremely condensed into the center of the atom. And when positively charged particles would hit it, because he knew that positive and positive repel each other, that's what would cause such great deflections. And those that passed by kind of close would deflect a little bit, and those that passed by a relative distance far away wouldn't really be deflected by it. So he basically believed that the foil was more like a net of all these atoms that were spaced out, and there was just a tiny region of space in the atom where all that positive charge was and where most of the mass was, and the rest of the atom was mostly just empty space. This later leads him to discovering the protons. So we know at this point, Rutherford's description of the atom was that you had that very dense nucleus inside of an atom, and that we had these electrons that are sort of moving around the atom. So you might actually see often the very popular Rutherford atom that kind of looks like this. You've got your nucleus, and then you have your sort of three-ring system, kind of like that. That's the Rutherford atom. In 1913, Niels Bohr, a young Danish physicist and a student of Rutherford's, came up with a new model. He proposed that electrons move around the nucleus, or orbit around the nucleus, in specific layers, or shells. This is commonly known as the planetary model. Much like planets orbit around the sun, the idea was that electrons orbit around the nucleus. Of course, people had asked, if the nucleus was positively charged and the electrons were negative, why didn't they all just fall into the nucleus? Well, he proposed that the reason for this is because electrons, which could only be found in certain energy levels, had a fixed energy and could not exist between the energy levels, but only at those energy levels. So, for example, you could find an electron on one of these orbits, but you couldn't find an electron in any space between the orbits. So the idea is very similar or analogous to, say, a ladder, right? If you wanted to go up a ladder or down a ladder, you can only move by standing or placing your feet at certain specific positions. You couldn't place your feet in the gap between these rungs of a ladder. And that's the idea of the electrons and energy levels. An electron can be found at this position with a certain amount of energy, or in another energy level with a certain amount of energy. But in order to go from one energy level to the other, it must gain or lose just the right amount of energy in order to change energy levels. So it cannot exist between energy levels. In fact, the energy required for an electron to jump from one energy level to the next is called the quantum. And the general idea is that the higher the energy level that the electron is found in, the farther away it is from the nucleus. Now, just to be clear, the energy levels, the spaces between the energy levels is not exactly the same size or equal in energy. In fact, it turns out that the energy levels are actually more closely spaced the farther we get from the nucleus. So as we get farther and farther and farther, they start getting a lot closer to each other. And obviously these very crepidly drawn circles. So in the ladder analogy, this kind of ladder probably would have been a little bit more precise. Something like that. So for the electron, the difference in energy decreases as we get farther and farther from the nucleus. And this planetary model worked out great in terms of determining the energies that electrons had at certain distances away from the nucleus. However, there were some complications. It turned out that other experiments started to show that electrons were not defined to a particular point in space. Instead, they would behave more like waves. So you would actually see something like this in measurements, which did not agree with Bohr's orbit theory. So after seeing this strange behavior of electrons, it turned out that we were soon going to give rise to a new quantum model of the atom. Enter Werner Heisenberg. Wait, no, that one's not it. Well, I already drew this one. So we'll just use this one. But if you really want to know what he looked like, there he is. But I need the space to write, so we'll keep my drawing. So Heisenberg was one of the argued father of quantum mechanics. That moniker's thrown around a lot between Max Planck, Werner Heisenberg, Erwin Schrödinger, Niels Bohr gets that title sometimes. But it was all based on the idea that these electrons were not necessarily particles or waves, but they had properties of both and neither. One of the principles that he's most popular for is the uncertainty principle, which uses this complex mathematics, but basically says that at any given time, when trying to measure an electron, you cannot know with certainty both the position of an electron and its momentum. In fact, the more you know about one, the less you know about the other. So let's kind of think of it like this. Let's say you were going to take a picture of you and some friends. So you take the picture. What happens is light, right, will hit your face, hit your body, hit everything, reflect, your camera lens will pick it up, and you get your picture. Obviously, the camera works a little more complex than that, but that's the basic idea. You get a very clear picture, you know exactly where everybody was and who was moving and things like that. But you're so big, and the light energy that hit you from the camera did almost nothing to you. So that's very easy to determine from measurement. But what if instead of taking a picture of you and your friends, you instead wanted to take a picture of an electron? Alright, so let's say you take the picture. What's going to happen is light is going to leave the camera and hit the electron, which is already moving extremely fast. But let's say you hit it. This particle is so small when compared to that of waves of light. They're very, very close. When the light energy hits it, the electron will absorb some of that energy and quickly change position and change its velocity, right? Thus changing its momentum before the light has even made its way back to you. So you measure the electron and you say, oh, here are its properties, except it instantaneously changed position and momentum at the moment of being measured. So yes, this atomic model starts to get very, very complex. And we're actually now going to turn to another scientist, an Austrian physicist with a perhaps very familiar sounding and very popular cat. Erwin Schrödinger took atomic models to a whole new level. He used the quantum theory to write and solve a mathematical equation describing the location and energy of an electron in a hydrogen atom. The newest model that we accept today, called the quantum mechanical model, is based off of mathematical solutions to the Schrödinger equation. And this is extremely complex for everyone. You don't have to worry about seeing any kind of math like this until your third year in college when you major in chemistry. You can see this under the course Physical Chemistry or Quantum Mechanics. So when we take this model and compare it to something like the Bohr model, it's similar in that it does restrict the energy of electrons to certain values. However, a complete departure to the Bohr model is the fact that the quantum mechanical model does not define an exact path that an electron takes around the nucleus. Instead, his equation just estimates the probability of finding an electron in a certain position. So in the quantum mechanical model, the probability of finding an electron within a certain volume of space surrounding the nucleus could be represented as a fuzzy cloud, where, say, the most dense region around the nucleus is where we have the greatest probability of finding an electron, and the less dense region, the less fuzzy area, would be where we would less likely find an electron. And it should kind of make sense that the farther we go from the nucleus, the farther away we are from the nucleus, the less likely it is that we'll find an electron because of its attraction to the nucleus. And because it's kind of hard to say where the electron cloud ends, generally we basically just limit our probability of where the electron is to 90%. Unfortunately, the shapes of these regions of space where the electrons can most likely be found are not limited to just spherical shapes or circular shapes. Some of them have very interesting, weird, very hard to calculate mathematical shapes. Of course, we'll learn that in the next lecture. And since we're a little pressed for time, we'll save the story of Schrödinger's cat for another day.